Alright, so today we're going to be covering early atomic theories, classic experiments, and future applications of atomic history. The first atomic theory was developed by Aristotle, who broke all matter into 5 elements: earth, air, water, fire, and ether. Ether is essentially what stars are made up of. These theories persisted until the 1700s, when Democritus popularized his own theory of how the atom works. First of all matter is made of atoms. This is pretty self-explanatory. Number 2, atoms can form physical connections. There are 2 connections that Democritus laid out: the ball and socket connection and a connection to environment. The ball and socket connection is used between atoms and can form compounds. The second one, between an environment, is the void space between atoms. Number 3, atoms are indestructible, solid, invisible, and constantly moving. The first part of this was disproved by the Manhattan Project in the 1930s, which showed that using a tremendous amount of force, an atom can be split apart. However, it does not happen naturally and can only happen synthetically. Number 4, atoms differ in size, shape, mass, and position. The first part of this is true. Atoms do differ in size and mass based off atomic number and atomic mass. However, the latter part of this is incorrect because water molecules are not more slippery and air molecules are not more light. So Democritus' ideas persisted until the work of other scientists led to the formation and revising of the new theory, which was called Dalton's atomic theory. So let's take a look at Dalton's atomic theory. Number 1, same as Democritus. All of matter is made of atoms. Again, pretty self-explanatory. Number 2, all atoms of one element are identical in structure and properties. This is called an isotope. Isotopes are essentially atoms that have one more neutron than they're supposed to. For an example of this would be carbon-12, and when you add one more neutron, it becomes carbon-13. Carbon-13 is used for radioactive dating, and it allows and essentially lets off a radioactivity. Number 3, atoms cannot be created nor destroyed, only rearranged. Antoinette and Marie Lavoisier proved this in their theory of the conservation of mass. Their work led to the basis of many other parts of this theory. Number 4, Joseph Proust proved that atoms of different elements combine in whole number ratios to form compounds, which is called the law of definite proportions, which essentially means that, say, a salt titration would have the same percent of salt left over after the reaction. This means that generally ratios just stay similar, which is why we balance chemical reactions. Number 4, when 2 elements combine, their ratios combine. This was called the law of multiple proportions and was formulated by Dalton himself. A good example of this is, say we have a compound that has 16 molecules of carbon and 2 molecules of oxygen. Another compound has 32 molecules of carbon and 2 molecules of oxygen. If we compare the ratios of carbon and oxygen, carbon has a 1-to-2 ratio while oxygen has a 1-to-1 ratio, proving that it'll always be whole numbers. Prior to 1897, scientists believed that atoms were made up of another particle that had a mass equal to that of a hydrogen atom. This would produce an ideal charge to atomic mass unit ratio. J.J. Thomson attempted to prove this in 1897. He used a cathode ray tube, which is a common component in older television sets. The cathode tube has 2 cathode plates, a positive and a negatively charged one, which determine where the light goes. When electrodes are shot through the cathode ray tube, it produces light, which is usually used to illuminate the back of a TV or something. But when the light's shot through, it should pass in straight if what the other scientists said was true. However, when Thomson tested it, the light bent like this line here toward the positive side, indicating that a part of it was negative. Also importantly to note that there has to be subatomic particles because of this bend. Also, it's important to note that subatomic particles exist because the speed at which the electrodes move was faster than the speed of a hydrogen atom. Speed is based off the weight of these atoms, and the hydrogen atom is the lightest atom of all the atoms. Hence, the fact that this is faster than that indicates that this has to be a particle smaller than that, saying that there has to be subatomic particles. So the next thing that was done after they determined that something existed. First of all, what Thomson did is he named this particle an electron because it had a negative charge. He then created what he called the plum pudding model. Essentially, this is an atomic model where there's the atom, and then around it is just peppered with electrons, kind of like plums in a plum pudding, hence the name. The next thing that they did after that was they did the Millikan experiment. Millikan experiment essentially was supposed to find the charge of an electron. What it did is it took an oil droplet and placed it between two positive and negatively charged electrodes. The charge of the electric field that was generated is a whole number that's a multiple of 1.592 times 10 to the negative 19th coulombs. And using that, he's found the charge of a singular electron, which he found to be 1.76 times 10 to the 11th. So one of Thomson's students was Ernest Rutherford, and what he wanted to do is that he wanted to prove that Thomson's theory was correct. So let's take a look at his experiment. All right, so here we have the Rutherford atom. So we're going to start it up. Essentially, what Rutherford did is he took alpha particles and shot them at a gold foil. If what Thomson said was true, all the atoms would pass through because it was negatively charged. However, let's start the flow and we'll see what happens. Note carefully that a lot of the purple particles are bouncing off of the atoms of gold foil. This indicates that there is a positively charged part that is repelling the atoms from moving. If we look at the proton count over here and we increase it to say 100, we see a lot more sporadic movement. This indicates that something's of positive charge here. We lower the proton count and we get 20 into 20 and we get very little interaction. This indicates that we have a positive charge at play, which was the proton. Rutherford went and added this to Thomson's model, creating what he called the nucleus that was made up of these protons. So going back now, we take a look at the last part of what the atom is made up of. That is the neutron. The neutron was found by James Chadwick, who worked in Rutherford's lab. Essentially, what he did is he took a string of alpha particles and bombarded them against beryllium. When he hit the beryllium with that, neutrons were released. Neutral charge was released. This indicated that a part of the particles had a neutral charge. What James Chadwick called it was a neutron. And a lot of other labs did this prior to him. However, he estimated that the mass of the neutron was about the same as the proton, which is a big thing because that makes up another part of the nucleus. So what's the future of all this stuff? Because this is early atomic history, right? So what happened in the future was they created Bohr's model because the plum pudding model was not exactly accurate, 100% accurate. It didn't take into place for all the nucleus and the protons and the neutrons, and Bohr's model really showed up how we put the order of the electrons in it. That gave rise to electron configuration, which shows how different atoms have different amounts of electrons in valence shells. This led to periodic trends, so we can show things like electron negativity, fifth ionization energy on the periodic table. And this idea really just leaves a primer for it. So essentially, that's it. For more learning, take a look at Bohr's model and the other stuff. And yeah, these are my sources, and this is essentially it. Thank you so much for watching.